Isaac Newton summarized the conclusions of his great predecessors and created a solid foundation for classical physics. This elegant theory is based on three famous laws of mechanics and the law of universal gravitation. These important laws allowed scientists to predict the positions and movements of celestial bodies with maximum accuracy. The third law of dynamics perfectly explains the mutual rotation of the Earth and the Sun around a common barycenter.
All right, let's begin. Today, we're going to dive into the fundamental laws that govern motion and interaction in our universe, the laws so brilliantly put together by Sir Isaac Newton. You see, this is the very bedrock of what we call classical mechanics. It gives us this incredibly powerful framework to understand pretty much everything, from a simple falling apple all the way up to the majestic orbits of the planets.
So, here's our plan. We'll start by looking at the work that came before Newton, the foundation he built upon. Then, and this is crucial, we'll define the idealized world, the specific framework where his laws even operate. After that, we'll get into the good stuff. We'll break down each of his three laws one by one. And to wrap it all up, we'll look at their amazing legacy, especially in astronomy, and, just as importantly, we'll talk about where they hit their limits. So, let's get started.
You know, it's really important to understand that Newton's work didn't just appear out of a vacuum. It was this grand synthesis, a truly masterful unification of all these different threads of observation and experimentation that had been carefully woven by the brilliant minds who came before him. And here you can see that intellectual lineage that led directly to Newton. You've got Kepler, who gave us these incredibly precise empirical descriptions of how the planets moved. Then there's Galileo, whose experiments on Earth started to formalize this strange concept of inertia. Huygens pushed the mathematics of dynamics even further. Newton's genius really was in seeing the universal principles that connected all of this. He formulated a single, coherent system that could explain it all.
Now, before we jump into the laws themselves, we absolutely have to understand the conceptual framework they live in. See, Newton's laws aren't just absolute truths that apply everywhere all the time. They are brilliant, brilliant approximations that work under very specific, idealized conditions.
So the first idealization is what we call the material point. We basically agree to treat a huge object, like a planet or even a star, as if it's just a single point in space that has mass but no size. Now, you might think that's a huge oversimplification, right? But in the absolute vastness of space, where the distances are just immense, this turns out to be an exceptionally good approximation. It lets us simplify these incredibly complex systems down to something we can actually calculate without really losing much accuracy at all.
The second condition, and this one is maybe the most critical, is the inertial system of reference. Newton's laws are only truly valid in a coordinate system that's moving at a constant velocity, meaning it's not speeding up, not slowing down, and not rotating. Just imagine you're in a perfectly smooth train car, moving on a perfectly straight track at a perfectly constant speed. Physics inside that car would seem completely normal, just as if you were standing still. That's an inertial frame. But the moment that train accelerates, or brakes, or takes a turn, things inside would start to move around on their own. That's a non-inertial frame, and suddenly Newton's laws, at least in their simple form, just don't apply anymore.
Okay, so finding a truly inertial frame is actually not that easy. In practice, astronomers use a kind of hierarchy of better and better approximations. A topocentric frame, just you standing on the surface of the spinning Earth, that's obviously non-inertial. A geocentric frame, centered on the Earth, is a little better, but it's still flawed because, of course, the Earth is orbiting the Sun. So a heliocentric frame, centered on the Sun, is better still. But for the absolute best precision in our solar system, we use the barycentric system. This is centered on the common center of mass of the Sun and all the planets combined. It's the closest we can get to a true inertial frame around here.
All right, with that framework established, let's finally get to the laws themselves. We'll start with the first law, which really defines the default state of matter, what an object does when it's just left alone, free from any external influences.
This is just a profound statement. What it's really saying is that motion itself doesn't need a cause. An object that's already moving will just keep on moving in a perfectly straight line at a constant speed, literally forever. It's only the change in motion, what we call acceleration, that actually requires a cause. And that cause, Newton tells us, is a force.
Now, the way we express this mathematically is through the conservation of momentum. Momentum is defined as the product of an object's mass and its velocity. And it's a vector. It has both a size and a direction.
So what the first law is telling us is that in an inertial frame, this momentum vector stays perfectly constant, completely unchanged, as long as the total external force on the object is zero.
So if the first law tells us what happens when there's no net force, the second law is the exciting part. It gives us the exact quantitative relationship between a force, an object's mass, and the change in motion that results.
The key phrases to really latch onto here are proportional and in the direction. This sets up a direct causal link. The change in the object's momentum isn't just vaguely related to the force, it is precisely proportional to it, and it happens in the exact same direction as the force you applied.
Now, for an object with a constant mass, this whole idea simplifies down to that famous equation you all know, F equals ma, force equals mass times acceleration. This just brilliantly illustrates the vector nature of the law. I want you to visualize this. You have a point mass in space. You apply a force vector to it, an arrow pointing in some direction. Instantly, an acceleration vector appears, and it points in the exact same direction. The length of that acceleration vector, how much the object's velocity changes, is simply determined by how strong the force is, divided by the object's mass.
The third law is what completes the entire framework. It describes the nature of forces themselves. And what it reveals is that forces never, ever occur in isolation. They always exist as part of a mutual interaction between two different bodies. This right here is one of the most fundamental principles of symmetry in all of physics. It's telling us that whenever one body exerts a force on a second body, that second body is, at the very same instant, exerting a force of equal magnitude, but in the opposite direction, back on the first body.
Now, the absolutely crucial point here, the thing that sometimes confuses people, is that the action and reaction forces are always an interacting pair. They're equal and they're opposite, yes, but, and this is the key, they act on different bodies. The force of the Earth pulling on the Moon is equal and opposite to the force of the Moon pulling on the Earth. They don't cancel each other out because one force acts on the Moon and the other acts on the Earth. And this brings us to a really beautiful, real-world consequence of the third law. While we all know the Sun's massive gravitational force is what holds the Earth in orbit, the Earth is simultaneously pulling back on the Sun with an equal and opposite force. Now, because the Sun is just so much more massive, its resulting acceleration is tiny, but it is not zero. This tiny acceleration actually causes the Sun to execute a small wobble around the solar system's barycenter. And this isn't just some theoretical quirk, it's a real observable phenomenon. In fact, detecting this wobble in distant stars is one of the main ways we find exoplanets.
So let's wrap this up by taking a step back. Let's really assess the incredible impact that this Newtonian framework had on astronomy, and then also, let's be honest about the boundaries of its applicability.
The legacy is just immense. I mean, Newton's laws literally transformed astronomy from a descriptive science into a predictive, physical one. See, Kepler knew how the planets moved, he had the equations. But Newton explained why they move that way, deriving Kepler's laws from his own fundamental principles. This new framework allowed us to predict the positions of planets and comets with an accuracy that was just unimaginable before.
And yet, for all their extraordinary power, we have to remember these laws are still an approximation of a deeper reality. As our tools for measurement have become more and more precise, we've reached a level of accuracy, especially when we're working in that very precise barycentric reference frame, where the tiny limitations of the Newtonian model actually become detectable.
To account for these very subtle but very real discrepancies, things like the tiny anomalous precession in the orbit of Mercury, we needed a more profound theory. And that theory, of course, is Albert Einstein's general theory of relativity. It completely reconceptualizes gravity, not as a force acting at a distance, but as the literal curvature of space-time itself. For the highest precision astronomy that we do today, Einstein's theory is the essential tool.
And this leaves us with a final thought to ponder. Newton's mechanics gave us this incredibly powerful mathematical description of how gravity works. But Newton himself was famously cautious about speculating on the underlying cause of this force. He famously stated, "I frame no hypotheses." His work was a monumental, world-changing leap in understanding the how of the universe, and in doing so, it paved the way for Einstein and modern physics to begin probing ever deeper into the fundamental why.
Thank you, friends. Strive for understanding and become wiser. See you soon.